Hello friends, today we will be discussing dynamic programming, which is another technique for designing algorithms for a certain specific class of problems. Now, the nature of these problems which we are trying to solve with dynamic programming is such that a solution to this problem can be obtained by dividing this larger problem into smaller subproblems. Solve those subproblems and then obtain the final result by combining the solutions to these smaller subproblems. You might be already familiar with such a technique when we obtain a solution by breaking down a larger problem into smaller subproblems and then solving those subproblems. Obviously, that is what we do in divide and conquer. But in dynamic programming, if we manage to find out that there are some overlapping subproblems, then we have encountered a DP problem. Now, we have to specifically understand what this overlapping subproblem means. Now, we'll try to find a difference between dynamic programming and this divide and conquer in the following ways. Now, in divide and conquer, obviously, we partition the problem into smaller subproblems, try to solve these subproblems and combine their solution to get the solution to the original problem. Now, it is important to note that a divide and conquer algorithm does more work than necessary. Why? Repeatedly solving common subproblems. We'll see that in a later example. A dynamic programming algorithm, on the other hand, solves each subproblem only once. It saves the solution of this subproblem in a hash table or some kind of an array and then reuses this solution to build the solution for the larger subproblems. And finally, reusing all these values up to solve the actual problem that we have in hand. Now, let's have a look at an example. We are familiar with the Fibonacci numbers, which can be solved with pair recursion. As you can see on the screen, there is this small code snippet which implements pure recursion to solve Fibonacci numbers or gives a solution to the Fibonacci numbers. Now, as you look at the code snippet, you can see that we have given the input to this code as 5, and let's try to dry run this code snippet and see how this divide and conquer technique basically solves this problem. So we call this code snippet by first calling fib of 5. Now, fib of 5, in order to find the solution of fib of 5, we need the solution of fib of 4, which has not yet been solved. Again, in order to solve this, the solution, or in order to get the solution for fib of 4, we need to obtain the solution for fib of 3 as well. But we do not have the solution for fib of 3. So we need to go down to solve fib of 3. In order to solve fib of 3, we need to solve fib of 2. Okay? Now again, we do not have a solution for fib of 2. So we go down and find the solution of fib of 1. Now the value for fib of 1 can be returned here. So we come back from this step and in order to get the value for fib of 2, we also need another call for fib of 0. So again, this is returned as 1 as in the earlier case. So we have got the solution for fib of 1, got the solution for fib of 0, so we'll return the value of fib of 2. Now, once we get the value of fib of 2, in order to solve it for fib of 3, we again need to call fib of 1. So we again get the same value here. Now, as we go upwards, we have to solve fib of 2 again in order to get a solution for fib of 4. So we again go down to calculate fib of 1, then fib of 0 again. So we get the solution for fib of 2, use it for calculating the value of fib of 4. Now, in order to solve the value for fib of 5, we got the solution of fib of 4, but we also need the value for fib of 3. So we go again through the recursive process. In order to solve fib of 3, we need to solve fib of 2, then we need to solve fib of 1 and fib of 0. So we get a solution for fib of 2 again. Then in order to calculate the value of fib of 3 again, we will have to use the value of fib of 1 again. So you might have observed, as I'll highlight here, that there are certain overlapping subproblems in order to find a solution to this Fibonacci series or Fibonacci number or the kth Fibonacci number. Now, you might observe on the screen that some of the sub-problems that were repeated by this divide and conquer technique are fib of 3, which is here, which can be seen here twice. Similarly, fib of 2, which occurs 3 times, and similarly fib of 1, which is repeated many times. So obviously, you can observe that we are repeating the certain steps. For example, calculating fib of 3, we are recomputing fib of 2, fib of 1 and fib of 0. Similarly, computing value for fib of 2, we are again repeating the same. So we can be a little bit intelligent in the sense we can try to avoid recomputing these values, and that is what dynamic programming is all about. It tries to save the values of smaller sub-problems that we have computed and then tries to reuse it later on. So if we look at this solution here, we can try to avoid recomputation of certain smaller sub-problems. So let's have a look at the implementation or a dynamic programming implementation of the same problem. So we maintain an array, as you have seen here. Since our input is 5, I'll be demonstrating it for 5, and we'll try to use a hash table or an array in order to restrict the number of computations or the recomputations that we are doing. So we store in this array values for the base cases for fib of 0 and fib of 1. Okay, so they have already been pre-computed and saved in the array. Now, if we want to find the value of fib of 5, how will we approach it? In order to find the value of fib of 5, before we try to solve it, we will try to see whether a value for this fib of 5 is already saved in the table or in the array or the hash table. Now, the value there is 0. 0 means that we have not yet computed the value. So we'll try to go down and try to solve fib of 4. Now, if we look at the array, again, fib of 4 is not computed yet because the value for fib result of 4 is 0. Again, if we want a value for fib of 4, we need to solve fib of 3. And when we look at the array, fib of 3, the value is not there because it's 0. So we go down and try to find the value of fib of 2. So before computing the value of fib of 2, we try to find whether we have already pre-computed the value in the array, but it is again 0, so we are not using it. Now, in order to find the value of fib of 2, we need to compute the value of fib of 1. Okay. Now, when we look at the array at this stage, fib of 1 has already been stored, so we'll try to use it. Okay. Similarly, in order to compute the value of fib of 2, we need to find the value of fib of 0, and we look at the array and it's already there. So we'll use the values of fib of 1 and fib of 0 to compute the value of fib of 2. So we fill in the value for fib of 2. Now, in order to compute the value of fib of 3, we needed the value of fib of 2 as well as fib of 1. Now, fib of 1 is also stored in the array. So we'll use it and compute the value of fib of 3, that will be equal to 3. Now, moving ahead, when we want to solve the for fib of 4, we have already solved fib of 3, we want to solve fib of 2. Unlike divide and conquer here, wherein we would have required more recursive calls, dynamic programming differs in the sense that before computing a value recursively for fib of 2, it tries to find whether it has already solved the value for fib of 2. So if we look at the array, fib of 2 has already been solved. So we do not need to get into those more recursive calls to get the value of fib of 2. We will use the value from the table. So we get that and compute the value of fib of 4, which is equal to 5. Now, in order to solve fib of 5 now, we have already computed fib of 4 and we need the value for fib of 3. Now, before computing the value of fib of 3 using recursive calls, again we will try to find whether we have already solved it in the array. And if we look at the array, fib of 3 already exists there. So finally, we get the value of fib of 5 and we store it in the array. So it is obvious that if we look at this result here, the number of recursive calls is way lesser than what we made in our previous example. If we go back to the previous slide, we can see that the number of recursive calls, as you can see there for fib of 3, we solved fib of 3 only twice in this case, in divide and conquer. But if we look at the dynamic programming solution here, you can see that we solved fib of 3 only once. Same applies for fib of 2 and fib of 3 and fib of 2, to be more precise. So if we want to write an algorithm for this implementation that we just did using an array, that is an implementation for dynamic programming, you can see this is on your slide, on your screen here. This is a simple implementation of dynamic programming for the Fibonacci numbers. You can see that we have saved the base cases, base case values here, fib result of 0 and fib result of 1, and then a simple loop is implemented to progressively reuse the values that we have computed in the array in order to compute values for the higher numbers. So the basic idea that you already got from the example here is to remember the answers for sub-problems already solved. So dynamic program, the essence of dynamic programming is that we need to remember answers to the sub-problems that have already been solved, and this process is known as memoization. Now the intuition is that we trade space for time. Obviously we use some more space in dynamic programming than in divide and conquer, simple divide and conquer. Why? Because, for example, you already saw that we used an array in order to store those intermediate values. That is, instead of calculating all the states, which take a lot of time but no space, like in divide and conquer, we take up space to store the results of all the sub-problems to save time later by not recomputing all those values. Majority of the dynamic programming problems can be categorized into two types. You will be facing two types of problems. Either they will be optimization problems or combinatorial problems. Now an optimization problem expects us to select a feasible solution so that the value of the required function is minimized or maximized. So we might need to minimize maybe the cost of a path, similarly for example, or we might want to maximize profits in for example scheduling algorithms and so on and so forth. Similarly, combinatorial problems expect us to figure out the number of ways of doing something or the probability of some event happening. We'll later on see some examples of these different techniques. Now there is a specific way of solving dynamic programming problems or designing algorithms for the dynamic programming problems. Now, or we can say there is a schema to be followed for dynamic programming. Now, the first step in that sequence is to show that the problem can be broken down into optimal sub-problems. So, if there is a problem which cannot be broken down into smaller sub-problems, obviously neither divide and conquer nor dynamic programming will apply. So it is important that the nature of the problem is that we are able to divide it into smaller sub-problems, solve those sub-problems and combine the solution to get the answer to the final problem. Another step, after we kind of find that the problem can be broken down into optimal sub-problems, we need to recursively define the value of the solution by expressing it in terms of optimal solutions for the smaller sub-problems. So we have to define a recursive statement which will solve the larger problem by combining solutions from the smaller sub-problems. The third step would be to compute the value of the optimal solutions, the small sub-problems, maybe using a bottom-up approach, or we can also have a top-down approach, but commonly we use the bottom-up approach. We'll later see examples using bottom-up as well as top-down. We'll also see the difference. So we find that a problem can be broken down into smaller sub-problems, try to find a recursive statement defining the solution, compute the values of these optimal solutions, maybe using a bottom-up approach, and we can also construct an optimal solution from the computed information. We can define the solution. Now the three steps that we just discussed, the first three steps form the basis of the dynamic programming solution to a problem. Now, if we need only the value of the optimal solution, for example, we do not need the fourth step. Now, the fourth step is needed only in case we want to define how we got the solution. For example, if we want to find the cost of the shortest path between one node and another in a graph. So, if we just want the value or the cost only, we don't need the fourth step in the earlier case, as we said. But if we want the complete path, for example, we need to go from node A to node B, then from node B to node C, and so on and so forth. In addition to the cost of the path as well, we also need the path. We need to we might need to store some additional information during the third step, during the recursive step, so that we can easily construct the optimal solution as well, besides the value. So, earlier I also told you that we have two approaches for designing solutions using dynamic programming. One would be the top-down approach. The example that I just discussed earlier for the Fibonacci numbers used a simple top-down approach. So, we write the procedure recursively in a natural manner, but modified obviously to save the result of each sub-problem, usually in an array or a hash table, as you saw earlier. Now, the procedure first checks to see whether it has previously solved this sub-problem. As I illustrated at that time, for example, we wanted to find a value for fib of 5. Before entering the recursion step, we try to find that whether we have already solved this problem or not, if we already have a value in the hash table or not. If it is there, then it returns the saved value, thus saving further computation at this level. Now, if it is not there, if we didn't find the value in the hash table, then the procedure computes the value in the usual recursive manner. Now, this implementation of dynamic programming, we can say that it is a recursive procedure that has been memoized using the hash table or the array. That is, it remembers what results it has computed previously. Another approach that we use for dynamic programming is the bottom-up approach. Now, this approach typically depends on some natural notion of size of a sub-problem, such that solving any particular sub-problem depends only on solving smaller sub-problems. Now, we sort the sub-problems by size and solve them in size order, smallest first. We'll later on see an example. It will be more clear at that point. So, when solving a particular sub-problem using bottom-up approach, we have already solved all of the smaller sub-problems its solution depends on, and we have saved their solutions. So, whenever we reach a particular solution, a sub-problem, we have already solved its smaller sub-problems. We solve each sub-problem only once, and when we first see it, we have already solved all of its prerequisite sub-problems. We'll see an example later on. So, let's have a look at an example demonstrating bottom-up approach. Now, we have a problem wherein we are given a number n, and we need to find the number of different ways to write it as the sum of numbers 1, 3 and 4. So, obviously, it is a combinatorial problem. It's not an optimization problem. For example, if the value of n is taken to be equal to 5, the answer would be 6. That is, there are 6 different ways of getting 5 with the sum of 1, 3 and 4, as is illustrated on the slide. So, 1 plus 1 plus 1 plus 1 plus 1 is 5. Similarly, 1 plus 4, 4 plus 1, 1 plus 1 plus 3, 1 plus 3 plus 1 and 3 plus 1 plus 1. So, there are total 6 different ways of getting the result 5 by the sum of 1, 3 and 4. So, this is just an example. Now, if we want to find a solution to this problem using dynamic programming, we have to define a sub-problem. So, let's suppose dp subscripted n is the number of ways to write n as the sum of 1, 3 and 4. Now, we need to define a recursive statement which solves this problem from the smaller sub-problems. Now, looking at these different solutions as are illustrated there, for example, if we take n equal to 5, so define the sub-problem, let dp of n be the number of different ways to write n, the input value, as the sum of 1, 3 and 4. Now, if we want to define it in terms of a recurrence, let's say that n is equal to x1 plus x2 plus so on up to xn. And if we observe in this sequence of sum, let's say the last number is 1, and if we take this 1 out, so let's represent the number of sums that end with 1 equal to dp of n minus 1. Similarly, we can represent the number of sums that end with 3 equal to dp of n minus 3, and similarly the number of sums that end with 4 be represented as dp of n minus 4. So the total number of ways of representing this n in terms of dp of n minus 1 and dp of n minus 3 and dp of n minus 4 would simply be as is shown in the slide down there. So in order to find the number of different ways we can represent n as the sum of 1, 3 and 4, we have divided this larger problem into 3 smaller problems. So the number of different ways to write n as the sum of 1, 3 and 4 has been divided into 3 smaller problems by or the sum of the solutions from 3 smaller problems. The number of different ways to write n minus 1 as the sum of 1, 3 and 4, the number of different ways of writing n minus 3 as the sum of 1, 3 and 4, and similarly number of different ways of writing n minus 4 as the sum of 1, 3 and 4. Then we can recursively solve this dp of n minus 1, dp of n minus 3 and dp of n minus 4 and so on and so forth. So the solution or a dynamic programming algorithm for this problem would be as is shown in the slide here. We define an array dp, okay. We save the base cases in that array for dp of 0, dp of 1, dp of 2 and dp of 3. So we have already saved that, as can be seen in the first statement over there. Then these statements that are visible on your slide over there, you reuse or first compute the values from these smaller sub problems, use these values to find solutions for sub problems, and then finally combine the solution of these sub problems to get the solution for the larger problem. Now this technique, the implementation here about takes a bottom-up approach and uses memoization to compute the results that have already been computed. We'll try to dry run this small code snippet and see how this basically implementation works out. Okay, we have these base cases represented by these small bubbles. So we have dp of 0, dp of 1, dp of 2 and dp of 3. We have the values stored as 1, 1, 1 and 2. Now in order to find the solution for dp of 4, we will reuse the values or will use the values of dp of 0, dp of 1 and dp of 2. Similarly, to find a solution for dp of 5, we will use the values of dp of 1, dp of 2 and dp of 4. Similarly, to find the solution of dp of 6, we will use the values of dp of 5, dp of 2 and dp of 3. It is obvious from these this example here that as soon as we see the problem, for example dp of 6 in this case, the top node, we have already solved all its smaller sub-problems. We have solved dp of 5, we have solved dp of 2, we have solved dp of 3. Similarly, if we want to solve dp of, for example, 7, we have already solved dp of 6, dp of 4 and dp of 3. You need to note that the input that we have taken here is n is equal to 8 for the earlier implementation. And finally, in order to compute dp of 8, we reuse or use the values of dp of 7, dp of 5 and dp of 4. We have already solved these smaller sub-problems. So this is a simple illustration of a bottom-up approach of implementing a dynamic programming solution. The next lecture, we will be discussing a more specific example for illustrating dynamic programming, and that would be multi-stage graphs. We'll try to find or implement an algorithm for dynamic programming, maybe using a bottom-up or a top-down approach. So thank you, friends. This would be it for today.